Dr. Fotis Sotiropoulos to serve as Dean of the College of Engineering and Applied Sciences and was elected as a SUNY Distinguished Professor. His research focuses on simulation-based engineering science for tackling complex, societally relevant fluid mechanics problems in energy, environment, aquatic biology, and for today's talk, human health. He's published over 200 peer-reviewed scholarly works in these fields, having been funded by numerous federal agencies, including the National Science Foundation, the National Institutes of Health, and the Department of Energy. The coronavirus disease pandemic of 2019, 2020, and of course 2021 has been responsible for devastating morbidity and mortality and an economic catastrophe throughout the world not seen in nearly 100 years. Social distancing and face masks are widely recommended by scientific communities around the globe in order to protect others and the wearers from spread of the virus until medical science can extinguish the pandemic through vaccination strategies, which will be the topic of the companion talk tomorrow at this same time. Unfortunately, certain politicians here and elsewhere have challenged these assertions to the detriment of many. Given his scientific background, Fotis is an ideal person to help us understand how computational models have elucidated the underlying physics of respiratory particulate transport during human breathing, speaking, coughing, and sneezing, and how medical and non-medical grade masks influence this process. I believe you will see today the scientific basis for why we should all be wearing masks if we come anywhere near others who might be infectious. Simply put, there are no alternative facts here. I predict understanding the physics of droplet transmission of infectious agents will speak volumes to all of you. As a final housekeeping note, if you have questions for Fotis, please use the chat box, which I will monitor and bring forward at the end of his talk. And with that, I turn the hour over to Dr. Fotis Sotiropoulos to speak about how far is far enough and can masks curb the spread of COVID-19. Fotis.
Thank you, Ken, for the kind introduction, and thank you all for taking the time to join this lecture today. Before I start, I wanted to give you a little bit of a background of how this idea for this lecture originated. In one of the numerous meetings that I had with President McGuinness and the senior leadership team as we think about how to begin to return back to normal as vaccines come back and so on, and building on the success that we had as a campus here in the last few months. I mentioned to our president the fact that I've been engaging with others here at Stony Brook in numerical simulations that show really how important masks are. And she suggested that maybe it's a good idea to give a lecture. So that's how this came about. I was a bit ambivalent as being the interim provost, giving a provost lecture right now in this, but then the president of the Senate, Richard Larson, suggested that maybe it's a good idea for administrators to actually talk about the research to the entire university. So I thought this was a good idea. So today, and we are starting, I think, a tradition, and it's going to continue tomorrow with the other lecture from Ken and the team from the School of Medicine. But not to worry, the provost lectures will not be hijacked by administrators moving forward. They will resume in virtual mode now that we know how to do it as before, starting from next semester, okay? So a little bit about before, I will be talking to you about recent research that we have done here at Stony Brook. And being Dean of Engineering and Provost doesn't really allow me too much time to do research, but I'm passionate about research, so I try to stay engaged. And I'm really fortunate to have a group of incredible collaborators. So I really want to highlight here that this is work that has been done by Ali Khosronejad, Professor Ali Khosronejad from the Department of Civil Engineering, along with Christian Santoni, Dr. Christian Santoni, and PhD students Kevin Flora and Jessia Zhang. They are the ones who have run those computations. They are the ones who have done this analysis. This is work that a few months ago, as the pandemic was started, and Lee and I started talking about how we can use some of the computational tools he and others in my group over a number of years have developed to really provide some insight about the use of masks into the turbulent airflow during respiratory events. So, this video that you see here, this animation, by the way, it's the simulation in a supercomputer of a human cough. And no, you're not spewing worms. This is not what's happening out of one's mouth. What you see here is a visualization of the turbulent airflow that is generated during coughing. These various structures that you see here, the little mushroom-like structures, hairpin structures, worm-like structures, are areas where intense spinning occurs in the fluid. This is a characteristic of a turbulent flow, and that's really what creates the complex flow that, as we will see, is able to transport aerosols and small particles in long distances. So my talk is going to be structured in three areas today. First, I would like, in the interest of telling you a little bit what I have been doing as a researcher in my previous life, I'll give you a brief overview of the work that I have been doing over the last 20 years. Then we're going to talk a little bit about literature, kind of a review of literature about why fluid mechanics is important in understanding the spread of COVID-19. And then I'm going to close with some of the results of the simulations. So starting, okay. So my work has focused in computational fluid mechanics, and fluid mechanics, by the way, is relevant in a number of areas. Anywhere that you have fluid, whether it is air, water, blood, there are many important applications across a number of fields that this happens. So I've been intrigued by a number of questions like, for instance, how can we optimally harness power from wind, tides, and waves? Right, wind turbines, tidal energy devices are devices that are interacting with the fluid, whether it is air or water, to extract energy. Or questions like how we can mitigate impacts of climate change. Extreme floods occur more and more frequently. Floods mobilize huge amounts of sediments in rivers. They tend to destroy infrastructure and so on. Can we develop predictive tools that we can kind of plan for the effects of extreme flooding and protect our infrastructure? On a more fundamental aspects of this, I've been fascinated by questions: how has hydrodynamics shaped fish evolution? Why certain fish look the way they are, why they swim the way they are, and so on. Turns out fluid mechanics plays a very important role there. Another area that we've done a lot of work on is the hemodynamics, the connection of blood flow patterns and heart disease. A lot of important issues here that connect actually fluid mechanics with biomedical engineering, medical devices, heart valves, and so on. And last but not least, what I'm talking to you today about is the spreading of respiratory viruses. So fluid mechanics is ubiquitous everywhere we look around us, and being able to simulate fluid flows in different settings can help us understand and solve many important problems. So what I have been doing in my career is develop computational methods that, and this is the only equations that I will show here. These are the famous Navier-Stokes equations that govern the motion of fluid flows. These are too complicated to solve by hand or analytically. They have to be solved on supercomputers. The big challenge here is, of course, and that's where my work has made some contributions, is to be able to solve them in complex domains involving fluid structure interaction. For instance, you have a fish swimming, the presence of the fish changes the flow, and so on. Be able to solve these equations in arbitrarily complex geometries involving very complicated phenomena. And what has really made my work possible is really this exponential growth of computing power. This is a graphic from Time magazine, which shows how computational power and the cost associated with it has grown since the 1900s. It occurred to me that this is where my career has been. I started using computers in the early 1980s when I started as an undergraduate student. At the time, the computer of my choice was something called VAX 11780. The computational power of this thing has already been surpassed by a number of older iPhone generations, right? So this is something that we used to carry in our pockets, but it's not even as powerful for iPhone computers that we have right now, right? So today we are at an era, at a time where we're building computers capable of reproducing the computational power of the human brain. And we keep moving forward with new paradigms, quantum computing, and so on. So this computational power has made it possible now to take on very complicated problems, which we couldn't even imagine. I couldn't even imagine when I started my career. So what I have done in my group over a number of years is develop computational algorithms, make a lot of advances in numerical methods for solving very complicated flows, develop computational tools that can take advantage massively parallel supercomputers and use them to understand, but also use them as a tool for scientific discovery. Typically in fluid mechanics, we do experiments. In many cases, though, experiments are not enough or are not able to give us the complexity that is involved. So having the ability to have computational capability of that magnitude is extremely important. So we have developed a code that we refer to as the virtual flow simulator. A number of students and postdocs have contributed to this, which is simulating real-life flows in engineering, environmental, and biological applications at unprecedented level of realism and resolution. And I'm going to show you very quickly some examples. So I talked about fish swimming, for instance. This is work we had done in collaboration with Harvard renowned aquatic biologist George Lauder, who had done some very impressive experiments of bluegill sunfish. Certain fish when fish want to escape danger, they don't start to swim linearly. They go into the sea start, and that's what gives them a lot of acceleration. And the fish who evolved the ability to do this were very successful in the ecosystem. So we did simulations to try to understand what the flow patterns are during this, and a lot of other work in fish hydrodynamics. The ability to simulate flows in natural rivers and streams. So can we go in a stream like that, which is an actual stream in Minnesota, build data, build computational models of the turbulent airflow to understand how contaminants and sediments are propagating in these environments. A number of areas of importance for a number of biological and engineering questions, stream restoration, environmental protection, and so on, can be addressed with these types of tools. Rivers are covered by sand, and when there is intense flow in rivers during floods, or when air flows over deserts, these sediments are mobilized. So we begin to, we have this spectacularly complex forms that occur, sand dunes. So it's very important for a number of regions to develop computational tools to predict how the sand dunes form in a turbulent flow. So I'll show you here a video of a simulation like this with, it's a turbulent flow over a sand bed starting initially flat, but as the flow develops, you see the sediments mobilize and forming these spectacularly complex sand dune forms. Again, these blue worms are the same types of worms that were coming out of the mouth of the person in the first video, right? They are swirling mini tornadoes that characterize the turbulent flow really here. Again, these are some of the first simulations. Actually, these are quite unique. These are unique simulations, the very first of their kind, coupling sand motion with turbulent flow and be able to predict forms very similar to what has been observed in nature. Another area that we're working more recently is wind energy, where we have developed computational tools to simulate flow in wind farms. This is work that we're now continuing here at Stony Brook, looking into offshore wind farm. But again, you see here simulations of turbulent flow in wind farms in complex terrain. We can make decisions how to improve the formation, the layout of these turbines, and so on. Really another example of how these types of simulation tools can be used and are being used today. And last example here is to really give you an example of the work we have been doing in cardiovascular flows, simulating medical devices like heart valves in anatomic models of the heart and the aorta. We've been looking at models of of the aortic valve and the swirling flow patterns. It generates a number of important connections with disease. These were some of the first flow structure simulations at this resolution that we've been able to produce. We developed computational models of the left ventricles with mechanical heart valves implanted there. And this have yielded a number of insights in biomedical applications. So I hope this gave you an overview of the work I have been doing in the last 20 years, let's say. I take a special pride that our work has been featured on a cover of a number of journals over a span of 15, 20 years here in the different areas that I talked about. And of course, as I said, I'm really grateful about a number of very talented PhD students and postdocs and so on, collaborators who have worked with me to really make this work possible. So moving on now to the main topic of my presentation, which is fluid mechanics and COVID-19 pandemic, right? So I want to spend a couple of minutes to highlight to all of you how important fluid mechanics is for a number of aspects of the disease, of the spreading of respiratory diseases and so on. So I believe it is widely recognized right now that the virus primarily spreads via respiratory droplets produced by exhalation, okay? These droplets really consist of saliva or mucus that originate from respiratory tract surfaces. So what you see here in this bottom cartoon is airways lined with mucus. And as we exhale, as we sneeze, as we cough, the airflow through the airways interact with that mucus, shears it off, creates droplets that are suspended, and then when you exhale, you actually see this. I understand it's lunchtime. This is picture on the top. It's not very appetizing, but this is it's a high-speed image of a sneeze, of a human sneeze. And one thing you see here is the range of particles that are created, okay? And it is very interesting that these particles contain a number, occur at a number of scales. So you can have large droplets. In fact, I think we all have seen others sneeze, and you know that there are droplets that are visible by the naked eye, but it's important to recognize that there are a lot smaller droplets that are created during this. So the process of creating these droplets begins, let's say, within the airways of our respiratory system, as airflow interacts with mucus. When we sneeze or cough or even breathe, we introduce these air droplets into the airflow. These droplets break up into smaller droplets, and then they begin to carry by the airflow the ambient air around us. So fluid mechanics is everywhere. Understanding the transmission pathways of SARS-CoV-2 virus or other respiratory viruses, understanding the fluid flow is extremely important, really, in the fluid mechanics aspects of this. In my work, of course, I'm going to focus on the moment in the processes after these droplets have formed and how they're transported by the airflow created by cough and breathing and so on. So in this cartoon here, you see actually little viruses in these droplets. As I said, we'll talk a little bit about sizes quite a bit coming up, but I want to highlight this point that these droplets come in all sizes and shapes. And depending on how big these droplets are, we may have different modes of transmission, whether it occurs through contamination of surfaces or through long traveling aerosols in the air. So let's talk a little bit about sizes. The key thing to remember is that an expiratory event will generate a dense cloud of fluid particles, which it's not 1 or 2 or 3 class sizes, it's continuum range. I have sketched here 3 particle sizes just to give you a sense. I don't mean to imply here that there are 100 micron, 10 micron, and 1 micron particles, right? This is just to give you a range of the orders of magnitude of particles. It's a continuum distribution. It's a complex cloud of these that are transported by the flow. So what is really important to remember, if we want to understand different modes of transmission, is how long it takes for these particles to settle. So forget about the airflow. Let's say that you have completely stagnant air and you introduce a particle of 100 microns or bigger, and you allow it to settle with the effect of gravity. This will take of the order of seconds to happen. On the other hand, a particle of the size of 1 micron or smaller, it could take hours or extremely long times. In fact, smaller particles is what we call aerosols, could stay suspended in the air for very, very long times. And they are so small that if inhaled, can penetrate lung tissues. So, of course, we have to think now the question, how big is the virus compared to these small particles? Can particles like that contain the virus? And I'll come to this question in a moment. The droplets, though bigger droplets, can settle before they evaporate and can contaminate surfaces. So let's take, I would like to take a moment to explain to those who may not be familiar with what is a micron and what is 100 micron. What does it even mean, right? So this is, I thought, a picture that highlight this very, very nicely. So what you see here is a human hair. Typical human hair diameter is anywhere from 50 to 180 microns. And then different things that are familiar, like sand beach, a grain of salt, a white blood cell. So if we keep going down, this is the red blood cell right there, 7 to 8 microns. So now compare, you have a size, a point of reference, something which is very, very small, like the diameter of the human hair, but you can begin to understand how small these small things are. And of course, we come here in the range of many respiratory droplets, the 5 to 10 microns that begin to get into the aerosol range. But the important thing is that the coronavirus is located down here. It's about 0.1 to 0.5 microns. So a respiratory droplet, which is 5 microns, could actually contain a number of molecules of virus in it. As a point of reference, look at the Zika virus. It's an order of magnitude smaller. This is the one transmitted with mosquito bites and so on. But that's really what the problem is. The transmission can occur. These coronavirus molecules are really small and can be contained by a number of droplets. Of course, the bigger the droplets are, right, the more molecules could contain. The smaller they are, the less molecules, but the smaller droplets can be transmitted for a long distance. So let's talk a little bit now about what do we understand about modes of airborne transmission. I think this cartoon gives you a good idea. So we talked about sizes of droplets. So bigger droplets, greater than 20 microns, they get to deposit fairly quickly within 1 meter. So they're about 3 feet, right? Intermediate droplets, 10 to 20 microns, they can go a little further. And then aerosols, these very small droplets, I guess, it has been recognized that they can travel very far. But what is interesting, though, is if you look at the social distancing guidelines, especially early on during the pandemic, when, remember, we all got the guidance that you keep 6 feet apart, you wash your hands, you're fine, okay? Masks were not discussed early on. There was a reason, perhaps, that was shortages of PPEs for hospitals and so on, but it's very clear. I mean, if you go back and you look at some of the WHO and CDC guidelines, it was keep your distance, wash your hands, and you should be in good shape. And in fact, what is interesting is WHO recommending about 1 meter distance or 3.3 feet. CDC was talking about 6 feet or 1.8 meters. But if you look into the literature, what was at least striking for me to find is that these guidelines are based on oversimplified science that is decades old. In fact, they track back, you can trace them back to papers by Wells in the 30s and the 50s, who looked at the deposition of some of the heavier particles. The assumption was that the main danger here is the heavier particles that deposit within that distance. So we're going to explore these guidelines with our computational tools in a moment. So I know that many of you are worried, or all of us are worried, what happens in toilets. Can we get transmission in toilets? This is images from work done by Buruiba from Buruiba's lab at MIT. High-speed image of droplets after somebody flushes the toilet. You see these ballistic trajectories of some of the heavier particles and this cloud of smaller particles. And in fact, in Buruiba's lab, they quantified that. So this is like after 5 seconds, you could expect to find finer particles suspended up to 0.8 meters, right? About 2.6 feet and so on. So really, if you go to a toilet, wait until the person has exited, and make sure you wear a mask. That's the important message here. So, and the thing that I would like the last thing I want to show you about from previous work, from existing literature, is this image, which is quite telling, because now it's a segue into discussing the flow that we're going to be simulating. So airflow patterns during expiratory events visualized by SLIR and imaging by LaVision. LaVision is a company that focuses on flow measurements and visualization. SLIR and imaging is a technique basically that uses slightest refraction of light. As a result, small temperature differences create small differences in density. They cause light to bend slightly, and this effect is exploited to create, to visualize the airflow patterns here that you see. So what you see here is actually currents that are moving upward. The body is hotter than the ambient flow. It causes buoyancy effects, but you also see this individual coughing, breathing, and talking, and you see these coughing jets that are created. A lot of our understanding of what the flow looks like is created from these types of visualization techniques. These techniques can only give us one slice through the flow, very difficult to get quantitative measurements, and it's difficult to look into longer distances, right? So that's where numerical simulation comes into play. So I'm going to move now to the last part of my talk, which is really the work we have done to simulate with high-performance computers human breathing and coughing. A brief introduction for those of you who are numerically savvy. I will try, I'm keeping this talk at a very non-technical level as much as I can, but I want to say here a little bit about the model. We solved the Navier-Stokes equations in Bussinesq form using large eddy simulation. The flows are turbulent we're simulating. We model saliva as an active scalar. We consider a range of sizes. We indirectly account for evaporation effects of saliva. We know that when saliva droplets evaporate, they get smaller in size. So we introduce this reduction in modeling in size through the simulation because smaller particles can go longer. So we want to have this effect. We have looked at a range of particles from 5 microns all the way to actually even 100 and 200. But I think here I will show you on 5, 10, and 40 is what I have here. The spatial resolution that we use to solve these equations is very, very fine. We have a grid with 650 million grid nodes. Without the computing power we have today, a simulation like this, it would be unheard. When I started my career, we could do simulations with 500 nodes and they were considered extreme. Now we have close to 1 billion grid nodes in very complicated simulations. And of course, the resolution in time, which is important, it's very fine. We are simulating 2 different ambient conditions because what happens to the droplets that are created and are introduced into the flow depends on the ambient flow. So whether we cough in a flow which is stagnant, in a room with no ventilation and no cross flow, is quite different than what's going to happen if we are outside taking a walk and there is a breeze around us. So we are considering indoor flow, stagnant flow. That when I say indoor flow in the subsequent videos, I'm talking about stagnant flow, where the only means to generate the flow is the expiratory event. And of course, we also consider outdoor flow in a situation where there is a mild unidirectional breeze that is taking place. We have taken into the simulation the anatomy of the human, the details of the mouth. The shape and the opening is very important in the structure of the jet that we create during expiration. We use very fine discretization for the mouth. We introduce the masks, and there again, for those of you who are numerically savvy, we use a diffused interface immersed boundary approach. We distribute a drag force where the mask is located that retards the flow. And we have used 2 different types of masks, a medical grade mask with very high drag force and a non-medical grade mask with a lower drag force. These are all values found in the literature. We have modeled both breathing and coughing. And what you see here is how we model breathing. Breathing under normal conditions is this sinusoidal function, maximum velocity, 1 meter per second, exhalation and inhalation. We breathe like that about 25 times per minute, what you see here. So we prescribe at the mouth of the person this waveform for the flow. Coughing, on the other hand, is just this pulse of cough. The velocities of coughing are much higher, 9 meters per second, the peak velocity, and then it dies out. We are only simulating one coughing event. So, all right, so now I can move to the results of the simulations. Talk about indoor coughing first. I will show you just a few examples of this because we have tons of data, but I think I'm going to use the points that are enough to make the key points that I would like to make. So 40 micron droplets. Remember, these are kind of in the heavy range of droplets. So this person coughs, and we look here at what happens to this cloud of particles that is created. By the way, this video is accelerated. It looks awkward in time because this is a number of minutes and I'm showing it in just a few seconds. So that's why it speeds up a little bit. But what you saw is that as the cough jet is created, these heavier particles begin to propagate forward, but because they are heavy, they begin to settle very quickly. So it turns out that their settling distance is about 5.3 feet within 3 minutes. You can see now the CDC guidelines of 6 feet. If our cough only had particles of that range or heavier, because the heavier the particles would be, the bigger, they would settle a lot shorter than that. And you could stay within 6 feet. You would probably okay as long as you made sure you didn't touch anything, right? Of course, if this person kept coughing continuously, then you're going to have a lot more particles that are introduced. But let's see what happens now if we go and we look at how droplets at 10 microns, which are evaporating in the process of the simulation to be 5.5 microns in size. Look at what happens in this event. It's exactly the same flow, exactly the strength of cough. Remember, our expiratory droplets have all these particle sizes all at once, right? So you can see here that the fate of this cough, of this cloud of saliva droplets is quite different. They don't settle, they keep propagating. And in fact, if you look at the very end of the simulation, the moment that the forward momentum of this cloud reaches 0, because if you cough once and it's going to propagate because of friction, the speed will be reduced. And at some point, it's going to become stagnant. So if you don't cough, if you don't breathe, and that's what we assume here, this is what it is, and then it's going to begin to settle. So that's what it looks like after we have reached this thing has stopped moving forward. From that point, this took about 5.2 minutes, and it propagated 9.3 feet. And what happens after that, it's going to start settling down, this single cough, right? It will take about 22 minutes for these particles to settle based on their size. So if you look at the total time it took from the cough, we are talking about more than 27 minutes. Somebody comes in a room, coughs up to within a radius of 9.3 feet. You have a zone of potential contamination that could last for half an hour. That's why it's extremely important to have cross ventilation, right? Here, it's not taken into account. If you have cross ventilation, these things will move out. So let's now turn our attention to simulate what happens when we wear a mask. Okay, so this is a medical grade facial mask. I should say that both a non-medical grade mask and a medical grade mask have the same effects. Of course, medical grade masks protect better, but there isn't, I mean, both masks actually will make a difference. So I'm not going to spend the time to go through all this. I don't have much time, but the key point is that this is what happens when you have a mask. These are the same 10 micron droplets that we saw before. And over the same simulated time, they reach a velocity, a stagnant velocity, of 0 essentially, after 8 minutes, propagating only 1.6 feet. Okay, the difference is stunning, actually. All right. Why does this happen? What do masks do? Actually, masks work in very complicated ways, but at the highest level, masks produce resistance to the flow. So there is flow does go through. There is leakage through the mask. First of all, all of us who wear glasses can feel the leakage that fogs our glasses, and you can see here in the simulation how flow goes over the face. There could be leakage below, and there could be leakage in the sides of the mask, depending on how it fits. In the simulation, the mask fits perfectly the sides. You see here these flow structures again, these worms and rings that are the turbulent flow structure. So you go from having this very complicated energetic jet that I showed you before to dramatically diminish its strength and forward-looking momentum, forward propagating momentum. You can actually see this very clearly if we are to plot how the overall kinetic energy of the flow, okay? The energy that is available for forward propagation of the aerosols varies without a mask and with a mask. So this spike here is the cough without a mask. You see how long time it takes to decay, okay? That's why these aerosols propagate very, very long distances. When you wear a mask, whether it is a medical or non-medical grade, there is a spike. It is much smaller, almost an order of magnitude smaller, and the decay is very immediate. That's why masks are very, very effective. So in summary, why do masks work? Unmasked coughing produces a highly energetic turbulent jet that can effectively transport virus-laden aerosols for very long distances. Face masks are able to dissipate the forward momentum of the jet, thus dramatically reducing the available energy for forward transport of aerosols. Low momentum leakage does occur through and around the masks, otherwise we couldn't breathe, right? There has to be some leakage. But because the momentum is very low, it stays close to the body. And you saw in the earlier video that I showed you these thermal plumes because of our heat of our body. So this will capture the droplets, the aerosols, and probably move them upward. Of course, if you have wind, as you'll see in a moment what happens when you have wind, this changes somewhat, actually quite a bit. But one point I would like to mention, and we haven't incorporated the simulations, some of the surgical masks incorporate fibers, and they have a lot of sophisticated ways of trapping very small particles through electrostatic effects. These are not included in the simulation, but I really believe that these effects are important, but in a way they're secondary. The ability of masks to dissipate the energy of the coughing flow, of the expiratory events, is extremely important. It's perhaps the most important aspect of reducing the... so in a way, actual masks could do better than what I showed you here, because we don't have these effects of masks being able to trap smaller particles in the simulation. So let's talk a little bit about indoor breathing. Remember, this is what the breathing looks like here that we prescribe. So this is again 10 micron droplets. So imagine having a person now just breathing in the room next to you. The flow here is much more organized. It's as we call laminar, because it's a lot slower than the coughing flow. But you can actually see again that without a mask, this normal breathing creates a plume of droplets that propagate. It's going to stop at some point. The simulation has not gotten far enough as yet, but it does get in. We have looked into 30 seconds of simulation, and it's about 4.6 feet. It's not going to keep growing. It's going to reach a steady state at some point, but it is really, you get an idea that even if you just simply breathe in a room, and you potentially create considerable contamination. So if you wear a mask, on the other hand, this is what happens here. The same type of breathing, the flow is slowed down a great deal, and it really, after 30 seconds, it has advanced only by 1.3 feet. Again, we can compare the mask and the non-mask breathing, looking at the same kinetic energy of the flow, the total energy in the flow that the act of breathing, inhalation and exhalation, is creating. Our lungs provide that energy, right? Our body is providing this energy into the flow and mobilizes the flow forward. What you see here when you're not wearing a mask, of course, the energy is much higher. You see these peaks and troughs here that relate to the inhalation and exhalation events. Obviously, when you wear a mask, actually the mean flow of the kinetic energy, the mean value is a lot lower. And in fact, it's pretty much dissipated very quickly. It stays at the fluctuations take place among a flat kind of peaks, right? Whereas for the non-mask case, it takes a long time to reach that plateau. Ultimately, this is not growing. It's the growth of the peak is diminished, as you can see here, and it's going to become steady and flat. But a lot more energy in the flow, takes much longer. So potential for contamination through aerosols is significant. So moving now to the last part of the simulations, we wanted to look at what happens when we cough outside, actually. So the difference here is that outside wind blows. So we just consider the case of a very mild wind breeze, 4.5 meters per second. So this is a simulation that involves the entire body right now. And there is a turbulent flow coming from upstream. You see here a slice through the flow. And what is shown here is contours of flow speed. So you can actually see how complicated the turbulent flow is. You see areas of reduced velocity because the flow comes from behind the body. Our body slows down the airflow. There's a complex wake that is created. You see the act of coughing here, the coughing jet. So look what happens now if we simulate 10 micron particles in a situation like this. They are able to propagate very, very fast. By the way, this is real time. The simulated time here is 0.6 seconds. Comparing coughing here, a mask, without a mask on at the top, with mask at the bottom, you see here that masks don't make that much of a difference. And the reason actually, in other words, in both cases, within 0.6 seconds, we have saliva particulates that are transmitted very fast. In fact, if you continue the simulation, this is going to disappear, okay? The wind flow is going to take it. So the bad news is that masks, and I'll show you why this happens. Actually, it is pretty obvious why it wouldn't happen, is that in an outdoor environment, they are not protecting us from contaminating others potentially. The good news is because the flow is turbulent, whatever contamination is dispersed very quickly, okay, and mixed with the remaining ambient flow. So why masks are not able to protect well in this is because of the leakage flow, right? So when we know that the mask leaks from our nose, right? We all have experienced that. If you have flow around the body, this leakage flow makes its way over the outer part of the flow, which propagates very fast. The saliva droplets are captured there and they begin to propagate very quickly forward, okay? So to summarize, what the simulation shows so far is, I mean, as a summary of the coughing simulations is in this kind of graph. No mask, indoor coughing, we have some of the finest particulates go up to 9.3 feet in 5.2 minutes. If you wear a mask, medical mask, this is cut down to 1.6 feet. Non-medical mask goes a little further. But clearly, if you wear a mask in an indoor environment and you stay 6 feet apart, you are actually very well protected from receiving any of these particulates. In an outdoor environment, it's quite different situation. There, you may want to wear a mask to protect yourself. Again, if you are in an environment, I don't know, like a political rally, for instance, who would go to a political rally in a COVID pandemic? But, you know, some people do. Or if you take a stroll in Central Park and there are a lot of people and on a Sunday, you may be, because of the effect I saw, there may be COVID molecules, virus molecules flying all over the place. Wearing a mask blocks them from you inhaling them, right? So concluding now, coming to my concluding points of my talk, the WHO and CDC social distancing guidelines were based on the early ones, on outdated science, focusing only on potential transmission through contaminated surfaces. These were focusing on the heavier particles that indeed deposit within 3 or 6 feet and contaminate surfaces. And that is a significant source of contamination because these are large particles with lots of molecules of COVID in them. Heavy saliva particles indeed settle within the recommended 6 feet CDC guidelines. However, the aerosols propagate many feet away from the body and could stay suspended in the air for a long time, okay? Of course, remember, whether you get sick or not depends on how much viral load you get, depends on how long you stay in this area of contamination and how many of these aerosols are there, how much viral load is present, right? So it's not a simple question. Here we're looking at the potential for getting exposed. Normal breathing is enough to generate suspended aerosols at considerable distance from the source. Masks, even simple ones, are effective in protecting others by dissipating the forward momentum of expiratory jets, especially in indoor environments. In indoor environments, if you wear a mask and you have good cross ventilation to be clearing all this potential accumulation of smaller particles of aerosols, I think things can be quite safe. And last point, when outside in the presence of wind, I think wearing a mask may not be, while indoor wearing a mask protects others, outside wearing a mask could protect yourself, especially if you are in crowded environments. If you're out taking a walk by yourself or a couple of people walking around you in a day that there is breeze and wind outside, it's unlikely that even you're not wearing a mask, anything is going to happen. But in a crowded environments outdoor, because of the effects I saw, it is a great idea to wear a mask. And that's why these masks have been recommended right now. So, and that is my concluding point. The bottom line, wear a mask, any mask, stay 6 feet apart to both protect yourself and others around you. Thank you.
Thank you, Fotis, so much. Very sobering talk. I learned an awful lot, particularly about the outdoors. We do have a number of questions. Perhaps the first one is about air conditioning indoors. Does air conditioning help by removing droplets, or does it make the situation worse by simulating outdoors and blowing the droplets around?
Yeah, so that's a great question. And in fact, as an area for moving forward with these computational tools, one can think of using these computational tools to try to investigate ventilated spaces and how you can design ventilation systems that could help clear the air. So I mentioned before that it's very important to have ventilation, cross ventilation in the space. This could come by opening windows or having air conditioners. If you take the air out, I mean, the moment you have an air conditioning inside in a room, this creates air currents and it's no longer a stagnant flow, right? So the important thing is, are you capturing the air, recirculating it, cleaning it, and introducing clean air? If you have a ventilation system that does this, then that definitely helps. And it's a condition that you would like to have. If you simply take the same air and you reintroduce it, of course, it's not, but air conditioners take the hot air, dump it out, you get cooler outside there. In general, ventilation systems, and we hear this right now in many of the restaurants and the hospitals and so on. A lot of people are spending money to really introduce ventilation systems with air filters, airplanes, for instance. So that's a really important thing of improving air circulation through a space. Because you saw some of these aerosols can stay suspended for a very, very long time. Okay, so the moment you have airflow and you take this air out, you can help clear the air there.
Two related questions. One asks about wearing the face shields. Does that help? And one asking if two masks, one over the other, is beneficial.
As long as you can breathe, the more masks you wear, the better, I guess.
Breathing's important. I can attest to that as a physician.
Yeah. So first about the face shield. I know this has been, and in fact, often you see around people wearing just a face shield. I can be very clear, face shields alone don't do anything. The reason is very simple, that there is a gaping hole under your face where the air, I mean, actually we could do a simulation to show this, but I can tell you that the only thing that a face shield can protect you is from some of the, if you have somebody near you who sneezes in proximity, some of the big projectile-like droplets, they get blocked by the face shield. But I think that there is clear air circulation, so some of the finer droplets, they could go out. I mean, it's definitely better than wearing nothing. I'm also worried in some situations whether wearing a face shield alone can be safe, how safe it is for the person who wears it. Because it goes the other way. Some of the particulates could get trapped under the face shield and stay there for quite a while, and you get to breathe them, where if you were not wearing the face shield, they would just be blown by the wind around you. So I think face shields alone would not really work. Face shields worn with a mask, especially for healthcare workers, okay, where the loads are very huge, could be very useful. Now, as far as two masks, I think one mask is especially some of the medical masks are more than enough. Of course, as I said, if you can put more masks there, fine. I mean, I remember watching early on in the pandemic a video on YouTube where this guy had put, I don't know, 10 masks and was trying to jog to demonstrate that he's actually able to do this and so on. But the more resistance you introduce, the better it is, obviously. But there is a point where, are you comfortable to breathe and so on?
With New York being the epicenter of great music, another member of the audience asks about musical instruments, particularly wind instruments.
Yeah.
Does that, what is the flow and the particle distribution like going through a clarinet or an oboe or another wind instrument?
That's a great question. I mean, another topic for simulation studies. But I can tell you that I think any event where you begin to exercise your lungs and you need to exert power to exhale, you increase these respiratory droplets. Now, if you use a clarinet and you blow through it, obviously some of these will be deposited within the instrument, but clearly you're introducing droplets into the ambient flow. And if you have an orchestra, let's say, playing instruments, taking instruments in and out of their mouth and so on, I think that definitely, I can't imagine that is something you want to do in a pandemic setting, really. I mean, you would definitely have considerable contamination there.
Okay. Another questioner asked about, occasionally we'll see people wearing a mask and it slips down below their nose. So the mouth's covered, but the nose isn't. Any simulation modeling of that about how much comes out the nose versus the mouth?
You don't need a simulation to see this. We all know how we breathe, right? We have studied breathing through the mouth here. Simulation, breathing through the nose, the main difference is the speeds are about the same, but the main difference is really that you get a jet that it is downward oriented, so it may change the dynamics a bit. But clearly, wearing a mask on your mouth or your chin, unless you stop breathing through your nose, it does no good.
One questioner asks about certain masks, particularly bandanas and things like that, will break up the large particles into smaller droplets. And as you've shown, smaller droplets are potentially more infectious. They spread farther, they stay in the air longer.
Yeah.
What are your thoughts on that? Can it be modeled?
Yeah, you can definitely develop more sophisticated, to be able to model this type of effect, you have to look into the structure of the material itself and how it impacts different classes of particles. It is certainly something that can be undertaken, but I think the important thing that the simulations have shown is that in addition to what happens to individual particles, an event like cough or sneeze or breathing is introduced. It's a collection of particles of different scales. It's a cloud of particles. And the big effect of the mask, that's why I think a bandana does good. In fact, maybe not as effective as a medical mask, is because it really decelerates significantly. It takes out a lot of the energy of this airflow that would propagate the aerosols further. So a mask that has the ability to break up bigger particles and introduce smaller particles after the mask, of course, is not good. But still, these smaller particles will have a lot less energy to propagate downwind.
Thanks, Fotis. So another question comes in about children. So we have heard the importance of schooling for school-age children, and really now beginning to say, well, the hell with all this stuff about, education from home, kids need to be back in school. And the justification / rationalization has been that children are less likely to spread the virus through their respiratory coughing, sneezing, and breathing. Have you done any simulation, or do you think it would be worthwhile seeing whether children have different patterns, different particle sizes, etc.?
Yeah, no, we haven't, but that's actually another good idea, because clearly the ability to spread the virus through expiratory events depends on the strength of your lungs and the ability to how energetic is this complex turbulent jet flow that you saw. So to that end, I think it would be really interesting to look at inhalation, exhalation, and cough patterns in children and adults and so on. That might be an interesting engineering-driven medicine collaboration, Ken.
What about humidity? You alluded to it slightly in the sense that I think it was a 10 micron droplet will, because of evaporation, go down to 5. Obviously, humidity, ambient humidity, would affect that. Has that been entered into the modeling?
So the humidity could be an important factor, and this especially for some of the smaller droplets that are staying suspended without that stay suspended and they evaporate before they settle. I mean, because some of the aerosols actually will stay there and begin to evaporate. And as they evaporate, they get smaller and smaller. Therefore, with available energy, could go further and further. So in the simulation, we haven't incorporated the physics of evaporation of droplets, but we have indirectly incorporated the effect of what happens that some of the droplets that start at 10 microns, based on experimental data we found, after a few minutes of simulation, we gradually diminish their size, which causes their settling velocity to change. And therefore, you have this effect. And we actually see very clearly that if you take, we have in one of the simulations I showed, if you have droplets that were of the size of 10 microns, and you don't do anything to incorporate for evaporation effects, they will stop after about 8 feet. If you allow them to evaporate, they will exceed 9 feet. So there is a clear effect, and it is obvious we have indirectly accounted for that in the simulation. We've seen the importance of this effect. Yes.
You mentioned that number of viral particles that one inhales is going to be important, and whether that exposure is truly going to be infectious or not. So I guess a question that comes from that is, are all particles created equally? Does a 1 micron particle versus a 10 micron particle have 10 times or the volume? I guess it would be the volume, not the diameter. But are very, very small particles, which you're going to argue are the most risky, are the very, very small particles contain a proportionate amount of virus?
Yeah, that's a great question. And I think that's why I said that from the simulations we have done, we cannot really quantify viral loads per se. We look at the potential for infection because there is important physics that determine this. If you think at what happens, airflow in the lungs, where you have mucus lining the lung, you have a very complicated interaction of the airflow with the mucus. Mucus is, by the way, a viscoelastic fluid. It behaves in very complicated ways. This interaction creates particles that then they exhale. As they come out of the mouth, you saw this image of the sneezing, where you get these sheets of mucus and this break up into droplets. So this is a very difficult question to answer, actually.
So we are at 1 o'clock, but I want to ask one more question because I have a suspicion that this is someone from my side of campus. It's been reported that ventilators that use a nasal cannula instead of a mask have infected hospital staff. Do you have any thoughts on the mode at which hospital employees are being infected, and does the kind of ventilation that's being used, you can still breathe through your mouth versus you can't breathe through your mouth because you have a ventilator mask on? Any thoughts on that?
Well, I mean, to the extent that I would like to know a little more about this, and maybe we can discuss this after this. But I would say that anything that changes the airflow patterns and exposes potential droplets, introduces droplets into the environment could actually make a big difference. So I would like to understand more a little bit about how this particular modes of ventilation might be changing the airflow patterns. Yeah, but definitely.
if you're interested, I'm more than happy to take you on a tour of our ICU where we have our COVID patients, giving you, of course, the proper protective equipment.
That will be great. That will be great.
Very, very good. So
to do that.
fascinating questions, great answers, great presentation. And so I would like to thank, on behalf of all of the 200 plus people who participated in this conference, thanks for a very stimulating and insightful talk. Thank you, Fotis, so much.
Thank you. Thank you all.